Hello everyone, welcome to my talk, and today I will be discussing about higher order functions in Python. Just a remark that the techniques I'll be using in this talk comes from the language F#. I get to use F# in one of my previous roles and I learned a lot from it, and I want to use some of these techniques in Python. My name is Haibin. I'm currently working as a data engineer in a hedge fund. I have a master's degree in mathematics. I also used to work as a financial engineer at a fintech company, as well as a business analyst at an e-commerce company. Just a minimum requirement that I need for this talk. I need you to know that a function, you can view it as a machine that takes inputs and returns an output. An illustration of such a concept is this coffee machine. Here you can see a coffee machine that accepts coffee beans and returns coffee as an output. And so you can view the coffee machine itself as a function that takes inputs, which is coffee beans, and returns output, which is coffee. And today, the three concepts that I want to discuss today are functions as input, functions as output, and partial application. Without further ado, we'll dive into these three concepts. So let's start off with functions as inputs. Take a look at this very basic function. Most of the time, when we input into a functions, our inputs x, y, z are simple data types. For example, it may be string, integer, float, date, list, set, dictionary, etc. Usually our inputs to functions are usually simple data types like these. But on the other hand, you could have functions as inputs to other functions as well. The analogy is the following. Imagine you have a big coffee shop. That needs coffee machines to run. Just now we know that the coffee machine is a function. The coffee machine is a machine, but it gets accepted, or it gets absorbed into a bigger machine or a bigger establishment. In this case, it is the coffee shop. The coffee shop, which is a large establishment, accepts a small machine, which is the coffee machine, to produce output. Here you have an example of a bigger establishment, a bigger machine, the coffee shop, accepting a smaller machine, the coffee machine, to produce output. So let's take a look at an example. Let's say that I have a h that accepts a smaller function f and returns f5. So if I have f, h is a bigger function that accepts a smaller machine, a smaller function f, and returns f5. For example, if I have a small machine g, gx equals to x plus 1. I throw this small machine g into h, it gives me 6. Basically, I calculate g5. It gives me 6. On the other hand, if I have a small machine k, kx equals to x times 100, and I throw k into h, it gives me h of k is 500, or I calculate k5 is 500. Let me show this in Python. So I have this hf. I have this h that accepts a smaller machine f. I define g, I define k, and I throw g and k into the machine h. It gives me 6 and 500. It gives me 6 and 500. So I have this small machine G, small machine K. I throw it into the bigger machine H, and it gives me the expected result. So it works in Python. So it's all fun and good, but on the other hand, how would this style of programming be useful? And to show how it would be useful, I'll demonstrate with two examples. One is Newton's method. Newton's method is a mathematical algorithm that helps you calculate the approximate solution to a function. And in fact, such an algorithm is already available in the SciPy library. For example, let's say that I have a function fx equals to x squared minus 3. Fx is 0 when x is square root 3, or x is approximately 1.732. And so, I import this SciPy library. I create this function fx that I want to optimize or solve. And I calculate the solution optimize Newton f5, where I choose a random starting value of 5. It's just a random number that I have chosen. And it prints a solution of 1.732. What's interesting about this code is that notice that the f is a machine by itself. This f is a function by itself, but it gets accepted into an even bigger machine. It gets absorbed into an even bigger machine, which is the Newton algorithm, the Newton machine, in order to create or generate results. A smaller function f gets accepted into a bigger function, which is the Newton function, to return a result. And that's a demonstration of how having functions as inputs could be helpful in code design. So for example, you take a look at this code and this small function f. I run it. It gives me a solution of 1.732. Notice that the smaller function f get absorbed into a bigger function, which is the Newton function. So that's one demonstration. Another demonstration is, for example, if I want to design an insurance product. How much should I charge for insurance? So let's say health insurance. I want to know how much should I charge for a customer for health insurance. So I want to have a pricing function. Maybe the pricing function depends on age. For example, it depends on age, how old is the customer and how much should I charge for it. And so the price depends on age. Maybe the price also depends on the probability of injury. How likely am I to get into a car accident or get into some sort of health emergency? So maybe the probability, which is a percentage or a floating number, would also determine the price that I should charge for my insurance product. But on the other hand, what if this probability depends on time? For example, maybe this year there's a lot of health emergency this year. Maybe next year it will be better. Maybe there's a lot of different variables. This probability is not a constant number. How should we account for that? It's not a fixed number. It changes according to time. Well, you could input a probability function instead. Instead of a fixed probability, a fixed number, now you have a probability function that depends on the date time and returns to you the chance or the percentage that you might get into an accident. So here you have a probability function, a smaller function gets absorbed or accepted into a pricing function. So a small probability function gets accepted into the pricing function, which is a bigger function. And that could potentially be a way of applying this code design of having smaller function accepted into a bigger function. Now let's get to the next topic, which is functions as outputs. Let's take a look at this example. Usually, most of the time when we return a result from a function, we also usually return simple data types. For example, string, integer, float, date, list, set, dictionary. Usually we return some of these as an output. But on the other hand, you can return a function as an output to another function. The analogy is the following. Imagine that you have a factory that takes in individual parts and spare parts and assemble into a coffee machine. So the coffee machine itself is a machine, but this machine, this function, is the output of an even bigger machine or an even bigger function. In this case, it is the factory. The factory, which is a large establishment, a large company, a large machine that creates smaller machines like the coffee machine as an output. So that is the analogy. So an example of how this style of programming could be helpful is interpolation. For example, you have, let's say you have data points, these red points over here. And you can connect these points together with straight lines. And once you connect them with straight lines, and you could, for any point x, you can draw a vertical line. You can draw a vertical line, and it hits the interpolated line, and it gives you an output y. So with a few data points, you are able to generate a whole function which are piecewise linear, which means you join them by straight lines, and you can read off the value from the curve. Of course, if you have a different set of data points, let's say you have these 4 points instead, then the same input x would give you a different output y. Let's try to think through how we could potentially implement this function. So this interpolation function, as you can see, this interpolation function depends on two things. One is the input x0. Whatever input x will change the output of y. And also it depends on the data sets that you provided. If you provide me this 4 blue points instead of these 5 red points, then the output y would also be different. So how would we implement such a function? So the interpolate depends on the original data set as well as the value being queried, which is x0. How should we implement this function? So the most easiest example is the interpolate function depends on the data set as well as x0. So interpolate depends on these two inputs and then it returns something. It's straightforward. A data set could potentially look like this. So this is the most easiest implementation. Another method of implementing this is to create an interpolate class that requires the data set to initiate the class. So you need the data set in order to initiate this class. And so once you have a class object, you can get the value at x0. So this is a more object-oriented style of programming. So in order to use this class, so let's say that I have this data set, I need to create an interpolation object here that creates an interpolate class with this starting value, with this data sets as the starting input, and then I call interpolation object dot get value at 2 in order to see the results. So this is a more object-oriented style of programming this capability, this interpolate function. But now let me try a third approach, which is a more functional approach. So I define an interpolate function that takes in the data set, and it immediately returns a get value function in the middle, where the get value function, I need to create it in the middle. What's the benefit of this style of programming compared to more object-oriented style? Is that the get value function is a smaller function that is returned by a bigger function interpolate. And also, so let's say that the code looks like this. I interpolate this data set. So I have an inner function created. And then I call this inner function at 2. Notice that I can directly use inner function. I don't need to find the method that is hidden inside an object. Previously, when I want to use the get value function, the get value is sort of like a method that is hidden inside the interpolation object. The get value function in the object-oriented style is hidden inside the interpolation object. But on the other hand, here, I don't need to create an interpolation object. This inner function thing is already a function. I don't need to find like a hidden method or some sort of method of that object. This is the function. So I don't need an additional object. I don't need an additional class to create this. I will demonstrate all 3 codes with Python examples. So I'll just show some pictures first. So imagine that I have this data set, for example. And I have 1, 7, and I have 5, 3. And the interpolation results in the middle here would include 2, 6, 3, 5, 4, 4. And these are the results that I expect from my simulation. And so let's try. So this is the more functional style of programming where I have the interpolate class. I have an interpolate class that requires the data set in order for me to initiate the object. And I need the data set in order to initiate this interpolate object. And once it is initiated, I can call this get value method or get value function that calls a value x. So how it is being used is over here. I have a data set over here. I have a data set, and I create an interpolate object over here. This is an interpolation object, and once I create this object, I will call the get value method inside the object. I will call the get value method inside the object. So let me try to run this. And it gives me 76543 as expected. So over here, I create an interpolation object, and I need to use the get value function hidden inside the object in order to get my interpolation capability. Now let's try a different approach, which is the functional programming approach. Here I have an interpolate function. And I have a get value inner function that is hidden inside the interpolate object, and I return the inner function instead. So notice that here I have I call the interpolate function on this dataset, and it returns me a function f. It doesn't return an object that I need to call a method inside the object. This functional method will return me a function. I don't need to access the function from a hidden method inside the object. This output f is the function. And so when I run it, it gives me 76543 again. It agrees with the previous method, But philosophically, it looks a little bit different. In the previous object-oriented method, the final function that I want is hidden inside an object. Whereas the functional method will give me the function that I want exactly how I want it. I don't need to access it through an object. Let's discuss about the last topic, which is partial application. The analogy is the following. If let's say you have a function or a machine that needs 3 inputs, but you only provide it with 2 inputs. So you still need the last input, the final input, in order for it to run. So seems easy. But you can also view of it in another way. If your machine needs 3 inputs, but you only provided it with 2 inputs, it means that the machine still needs that one last input, or you can think of it as a brand new function or brand new machine that still lacks that one final input in order to run. It becomes a brand new machine, a brand new function that is still lacking that final component. How would this style of thinking help in programming? So take a look at this example, fxyz equals to x plus y plus z. If you put 1, 2, 3, it gives you 6. But if you provide it with only 2 inputs, you will get a type error that says your function is still missing one last requirement z. This is in Python. But on the other hand, if you use the lambda notation definition, f accepts input x, input y, input z, and returns x, y, z. Then, if you call your result f123, it gives you 6. But if you give it only 2 inputs, it still compiles. f12 will give you a result. This result is actually a partially completed machine, a partially completed function. It's a brand new machine that still lacks that final component. It's a brand new machine that still lacks that final component. So this code actually compiles. It is a valid code. So you can think of this machine F that accepts X, Y, Z and return a result. If you throw 1 input, then it still needs 2 more inputs. If you throw 2 inputs, x, y, it still needs the final component z to return you a result. And of course, if you throw in everything, it gives you a result. Every step in the middle, there's no compilation error. But you just need to be aware that when you write fxy without a z, technically this compiles, but it actually returns you a partially completed machine or a machine that still lacks that final component. So an alternate way of defining this function f would be something like this. F returns an inner function. Instead of using lambda notation, I could use this notation instead. F returns an inner function. What does this inner function do? This inner function accepts y and returns a second inner function. What does this second inner function do? This second inner function accepts the final input z and returns the result. So f returns an inner function, which returns another inner function, which returns the final result. This would be a slightly different implementation compared to the lambda notation. The lambda notation also works, but this would be a more traditional Python code. So let me do some Python demonstration. So take a look at this example. If I have f123, it gives me 6. But if I only provide it with 2 inputs, it will give me an error. So you can see over here that it is missing the final input z, and so it is, and so it is, and so it leads to a compilation error. It leads to an error. But on the other hand, if I define f using x lambda y lambda z equals to x plus y plus z, and I provided it one input, two inputs, or three inputs, all three of these compiles nicely. And it will run and it will produce results. Let me try. So if I input 1, 2, 3, it gives me 6. But if I give you 1, 2, it gives me an inner function. If I gives you f1, it also gives me an inner function. So all of these compiles without resulting in error, compared to the previous code where it will produce an error. An alternate way is to write your code in a form like this. And let me run it again. And you can see these three results are actually right here. All three of them compile. All three of them works. There's no compilation error. There's no error. It runs. It's okay. But you just need to be careful that, for example, result number 5 and result number 6, these actually result in partially completed functions or partially completed machines that are not yet completed. It compiles, but you just need to make sure that these are actually not numbers. These are actually partially completed machine or partially completed functions. And now I want to get to SKI combinators. There's a branch of mathematical logic as well as computer science called lambda calculus. But for our purposes, take a look at these functions that I've created. B, D, and O. These are just a few examples that I've chosen. So you take a look at B, for example, where B, X, Y, Z is X of Y of Z. You can think of it as an analogy like this small fish gets eaten by this bigger fish, which gets eaten by this bigger fish, which gets eaten by this bigger fish. In this case, you can see the input Z is an input to the function Y, which the whole thing gets eaten by the function X. So these are just functions that I've chosen. A few questions naturally arise. Are these even valid expressions? Like, do they even make sense? Are they well defined? And also, what are some of the dependencies between W, X, Y, Z? Like, which of them goes to which one? Which is the input of which one? Do they even make sense? So I can certainly write down expressions like these, and expressions like these are part of a lambda calculus. And in fact, all of these calculations, all of these expressions are related to, in particular, three of them are quite important, is the SKI, where the SKI are defined as such. And let me rewrite this SKI in lambda notation, where as mentioned before, I want to use the lambda definition so that I can have partial application. I want this feature. In my code. And so if I rewrite my SKI in this notation, I slightly simplified this so that it's easier to understand. And so, in fact, I can express any lambda expression. Any of these expressions, B, D, O, any of these expressions can be simplified using S, K, and I. So how would I describe this, or what would be an analogy? The analogy I would choose is the number game analogy. Think of an example. For example, you start off with any number, take the first digit, take the first digit and you multiply it by the rest of the digits, and you repeat and repeat it again. Eventually, if you continue this process, your number will get smaller and get smaller and get smaller. You continue this process, your number will get smaller and smaller. For example, 9,27583. You take the first number 9, you multiply with the rest of the number, it gives you this 248,247. And then starting from 248,247, you cut off the first number 2 and you multiply it with the rest, you get a slightly smaller number. And then again, the next step, you take the number 9 from 96494 and you multiply again, it gives you this. Again, you continue this 58446, it gives you 42230. So the more steps that you do like this, your number gets smaller and smaller. So this would be an analogy of how the process works. This is to give you an analogy or give you a first exposure of how it works. So for example, let's say this simple function txy equals to yx. There is this website called Angelfire Combinator, where they list all of these functions on the left hand side, all of these simple functions on the left hand side, and you can reduce all of them to using s and k and I. In this case, they are a little bit strict. They restrict to s and k only. And so you can see that all of these functions eventually get reduced to only s and k, and maybe I, s and k. So let's do a demonstration. Let's say that this txy equals to yx. This t accepts two inputs, x and y, and returns yx. My goal is to show that t is equals to this expression, this sk sik. So let's start off. For example, I use tx. Tx is equals to this. Since I copy and paste it. And because of the property of s, I'm allowed to do something like this because the definition of s. And the next step is because of the definition of k, I'm allowed to do this. And then afterwards, I throw in the number y. I throw in the second number y. I throw in the second input y. And then because of the definition of s, I'm allowed to do this. And because of the definition of I can do this. And then because of the definition of k, I can do this. And in the end, I see txy is equals to yx. So you can see the analogy between these processes. So let me start from the top. You can see I use the first letter S, K, and then S, I, and K. And then to show that T is indeed equal to this. This process is a little bit similar to the numbers game example that I showed you just now, the numbers game. You take the first number and then you do some operation. You take the first number, you do some operation. You take the first number, you do some operation. It feels kind of similar. Of course, the technical details is more complicated than that, but it feels kind of similar. Let's try another example. Could you do something like this? Gy equals to y of y. Can a function accept itself as an input? Would it even be possible? Would it even make sense? Maybe in very specific situations in our case. For example, if let's say I have the identity function ix equals to x, and I input gi, then of course gi is just I of I, which is I. and it returns the function I. Let me do some demonstration in Python. So for example, over here I have txf equals to fx. I can also define it in the following form. And so if I run these codes, if I run this t with this input and this input, it gives me 101, 201, 301. These three inputs will give me 101, 201, 301. And on the other hand, if I try these three inputs, it will give me these three results instead. If I give you these three inputs, it will give me these three results instead. But on the other hand, I could also define my function t using only s and k. As you see over here, sk, 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 and I. And I run it again. You can see that the ski version gives me the exact same result. It gives me the exact same result. You see that the normal version, the simple version over here, and the ski version agrees in the output. And also, another example is you have gy equals to yy. Can a function accept itself as an input? Let me run this. And in fact, in this very special situation, yes, it can. The identity function just returns itself, you I of I. It gives you I itself. In this very specific situation, it can. But maybe not for more general situations. And in fact, even the identity function, the I function from ski, the identity function can be expressed with skk. So let me run this. So you can see that the identity function I1, I2, I3 is just 1, 2, 3. But a different version, which is the skk version, would also achieve the same result, which is 1, 2, 3. So what's the takeaway from all of these? The takeaway is that having functions as inputs and functions as outputs to other functions can be a powerful tool that will help us in our code design, software design process. But on the other hand, once you allow functions as inputs and outputs to other functions, you open up a huge Pandora's box that you need to deal with all the SKs, SKIs that we have shown just now. That also involves a lot of lambda calculus, and there's a lot of thought process that's going on. And it helps you appreciate the thought process that is going on at the language design level. Imagine the language designer have to deal with all of these at the implementation. And also this style of thinking also encourages you to think in terms of dependency. Which function depends on which one depends on which one, etc. It trains your mental strength a little bit. It encourages you to think a little bit more and think about your software design as well as dependencies. It trains your mental strength a little bit. And so, summary. We explored three concepts: functions as inputs, functions as outputs, and partial application. And also the implication that once you allow functions as inputs, functions as output, some of the really messy, like the Pandora's box that is open, once you do allow such functions as inputs, functions as outputs, you start getting all the SKIs and all the complicated things that also comes attached with it. And it helps gives you some appreciation of the language design. And if you have any questions, feel free to leave in the comment section below. And thank you very much for watching.